Hello guys, and welcome to another video. Today we're going to be looking at the introduction to real number system. In fact, the video is going to be a little bit longer, but don't worry, after watching everything you will get to know the general overview of what real number system is all about. So without further ado, let's get right into it. And before we start with the real number system itself, let's consider the two main categories of numbers. The first one is real numbers, and the second one is imaginary numbers. Now, to understand these numbers better, let's consider the following set of numbers. Let's say we have 2 and 5. Now, all these two numbers right here are real numbers simply because we can represent all of them on the number line. Now, check this. As soon as I attach I to this 5 right here, it is no more real but imaginary, simply because we cannot represent this number right here on the number line. Now, if you are wondering what this I is, let's consider it. I is basically square root of -1. Now, if you use a normal calculator, just like what I have right here, to compute what this one is, in fact, it's basically going to give you math error, meaning that the number is not real but imaginary. All right. So now that we have a fair idea about real numbers and imaginary numbers, let's group the following into real and imaginary. Let's say we have the way I, 20, 2, then let's say 4i minus 30. And we are asked to group this according to real and imaginary. Of course, any number that we have I in it is imaginary. So this right here are all imaginary numbers. And those without I are real numbers. So we have this, and this number right here. So that is basically it. So now that we have a general idea, we can now move on to what real numbers are, because our focus is only going to be on real numbers. All right, so real numbers. Real numbers are also represented by capital R. So whenever you see capital R in math, it basically means real numbers. We have two main categories of real numbers. In fact, the first one is rational numbers and irrational numbers and irrational numbers. Now, what is the difference between rational numbers and irrational numbers? Basically, rational numbers are numbers that can be expressed in the form a divided by b, and of course b should never be 0. In other words, rational numbers are numbers that can be expressed in the form of fractions, whilst irrational numbers are numbers that cannot be expressed in the form of a fraction. Now, before we come to an example of rational numbers or irrational numbers, let's consider some types of numbers that are found under rational numbers. The first one is going to be whole numbers. Whole numbers. Now, whole numbers are represented by capital W. Then next we have natural numbers. We also call it counting numbers, so natural numbers. And lastly, we have integers, which is represented by capital Z. In fact, natural numbers are represented by capital N, and it is also known as counting numbers. Now let's look at the set of whole numbers. Whole numbers, which is represented by W, is equal to 0, 1, 2, 3. In fact, it keeps on going forever. It doesn't end. So these are the elements in the set of whole numbers. Now, natural numbers. Natural numbers, in fact, the set of natural numbers is 1, 2, 3. Then it also keeps on going up to infinity. Now you notice that the difference between whole numbers and natural numbers is that whole numbers start from 0 and natural numbers start from 1. But in actual fact, all the elements in natural numbers can be found in whole numbers. So basically, we can say that natural numbers are subset of whole numbers. That means that all the numbers in the set of natural numbers are found in the set of whole numbers. That is what it means. Now let's consider integers, the set of integers. Integers, which is capital Z, is equal to, in fact, that one also starts from a point where we don't know and then comes all the way. We have -2, -1, 0, 1, 2, and it also keeps on going up to infinity. So look at it carefully. If we take a close look at the set of integers, we can clearly see that the elements in the set of integers are made up of the set of both positive and negative whole numbers, including 0. So we can also write this: natural numbers and whole numbers are subset of integers, like that. So we also have this statement that holds for these three sets. So all these are numbers that can be found under rational, and we are saying that rational numbers can be expressed in the form of a fraction. So let's take a look at this number right here. Let's say we have this one. 1 is the same as 1 over 1. We can also express that as 2 over 2, okay? And still we can see that it is of the form A over B. In the same way, if we pick this 0 right here, 0 is the same as 0 divided by 2. It is also the same as 0 divided by, let's say, 50, and so on and so forth. But this number or the denominator shouldn't be 0. That is the case, right? So basically, all these numbers can be expressed in the form of a fraction. If we take 2, for instance, 2 is the same as 2 over 1. It is also the same as 8 over 4. It is the same as 16 over 8. And all these are giving us 2. And of course, they are in the form of A over B. So basically, we now know why these numbers are rational. Now let's consider irrational numbers. What are some of the numbers that are considered irrational? Example is this number right here, pi. Pi is actually equal to, let me use my calculator for that really quick. Pi is actually equal to 3.141592654. Then it keeps on going forever. It doesn't end. So why are we saying this number is irrational? This number, we cannot express it in the form of a fraction. Why? Now, there are two cases that we need to consider for a number to be irrational. The first one is if the number is non-recurring, at the same time non-terminating, then we are saying that that number is irrational. Now let's consider the digits for pi. We have 3.141592654, then it keeps on going forever. We can see that with all these digits, there is nothing like recurring, right? None of them is recurring. Then it is also not terminating. It doesn't end. It keeps on going forever. Another example is E, the value for E, which is a constant. If you use a calculator for it, you are going to be getting 2.718281828, and it keeps on going forever. Now, if you look at the digits right here for E, some of the digits appears to be repeating, but ultimately they are not. Look at this. We have 28 right here. Even though it appears to be repeating, but it's never repeating, right? So it is non-recurring and non-terminating, therefore it is irrational. Another example of irrational numbers are square root of 2, square root of 3, square root of 5. In fact, square root of all prime numbers are irrational. If you use a calculator for them, you'll be getting numbers or digits that are non-recurring and non-terminating at the same time. The key thing is that if one of these non fails, then it is rational. So square root of all prime numbers, if you have forgotten prime numbers, A prime number is a number which has two factors, 1 and itself. Now, another numbers that are irrational are square root of the product of two different prime numbers is also irrational. Example is, let's say we have square root of 3 times 2. 3 is a prime number, 2 is also a prime number. Square root of the product of two different prime numbers is irrational. This will give us square root of 6, and square root of 6 is irrational. If you use a calculator for this, it will give you digits that are non-recurring and non-terminating at the same time. So basically, that is that. Now let's consider this question right here. Sort the following into rational and irrational. The first one is 0.325. Now, if you look at this carefully, we can see that it is non-recurring, all right? And because it is ending here, it is terminating. So it is non-recurring and terminating. Therefore, it is rational. This number is rational. In fact, for it to be irrational, they all have to be non-recurring and non-terminating, right? Because this one fails, it is rational. Then here we have 0.666. In fact, it keeps on going forever. So we can say that it is recurring and it is non-terminating. It is non-terminating. So therefore, it is rational. All right. Then we have this one 0.09090, and it keeps on going forever. So with this, it is also non-terminating. It doesn't end, and at the same time, it is recurring. So you see, it is recurring 9090. So it is recurring. Therefore, it is going to be rational. Now let's consider the last example. We have 0.7322333435. Even though this side appears to be recurring, but ultimately it is not recurring. Therefore, we see it doesn't end, it is not recurring. So we will say it is non-terminating, it doesn't end. And again, it is non-recurring. Therefore, it is irrational. All right, let's look at how we can change recurring decimals or terminating decimals to common fractions. And we have example right here. Change 0.11111 up to infinity to common fraction. So let's start. In fact, the very first thing we want to do is that we will set this decimal number right here to any variable. In our case, I will say x is equal to 0.11111 up to infinity. And this time we can call it equation 1. Again, we would like to generate another equation in such a way that we will shift the decimal point right here to, let's say, this side or even more. So what I will do first is that I will say equation 1 times 10. And this time, equation 1 is going to be 10x is equal to, if we multiply this number right here by 10, obviously we are going to shift the decimal point right here to this point. So we are going to have 1.1111, and it also keeps on going up to infinity. And this time we can call it equation 2. Now check this. The reason why I multiplied this number right here or this equation right here by 10 is that I wanted to shift the decimal point to a place that after the decimal point in equation 1, the digits right here will be the same thing as the digits right here. And if that happens, in fact, we can actually subtract equation 1 from equation 2 to get our fraction. So let's do that. We will say equation 2 minus equation 1. And on the left-hand side, obviously, we are going to have 10x minus x. Then the right hand side, we are going to have the whole of this, which is 1.111 up to infinity, then minus this right here, which is 0.1111 also up to infinity. And on the left hand side, we are going to have just 9x, and this is equal to, and let's pay attention to this. Here we have 1.111 up to infinity minus 0.1111 1 also up to infinity. Now we are subtracting. Now, because all the numbers right here are the same as the numbers right here, actually, if you subtract them, you end up getting 0, 0, 0, and so on. Then we put our decimal point, we have 1 minus 0, which is still 1. And obviously, we can see that 1.000 is still 1. So that means on the right-hand side, we'll be left with just 1. We are looking for x, so we will just divide each side of the equation by 9 so that this and that will go. And finally, we are going to have our fraction, which is x, is now 1 over 9. And we are done. And the truth is that if you use a calculator for this, you'll still be getting this back. So that is pretty much it. Let's look at the second example. Now, with this second example right here, we want to change it to common fraction. In fact, we can clearly see that the 222 is the part that is recurring. So let's go ahead and then do that. First of all, we will let the fraction that we are looking for be x, and that is equal to 3.222 up to infinity. And this time round, we would like to shift the decimal point in such a way that the new equation that we will have, all the digits after the decimal point will be the same. So to do that, in fact, I know that after the decimal point, we have 2 right here. As soon as I move this decimal point to this place, we will still be getting 2 as the digits after the decimal point. So let's say if this is our equation 1, then I'm going to say that equation 1 times 10. And if you do that, in fact, on the left we have 10x, then on the right hand side, if we multiply this one by 10, obviously the decimal point will come here. So we will have 32.222 up to infinity. And this will be our equation 2. And this time round, we can subtract equation 1 from equation 2. And if you do that, in fact, on the left hand side, we have 10x minus x, which is basically 9x. And this is equal to, now check this, on the left hand side, we have 32.222 up to infinity. Then right here, we have 3.222 up to infinity. Now, the fact that the digits right here after the decimal point are the same means that they will cancel each other. So we'll be left with just 32 minus 3, which is 29. And next, we are looking for x as our fraction. So what we will do is that basically we will divide each side of the equation by 9 so that this and that will go, and we are left with x is equal to 29 divided by 9. Of course, we can change this one to Mace number, which is obviously 3 whole number 2 divided by 9. 9 times 3 is 27 plus 2, 29. 29 over 9. So that is our answer right there. Next, we have this right here. It's a little bit challenging, but don't worry, we are going to go through. We have 0.431431, and it also keeps on going up to infinity. So we can clearly see that 431 is repeating. So let's start. Of course, always we will let some variable. This time around, I will say m should be equal to 0.431431 up to infinity, and this will be our equation 1. Don't forget that m is the fraction that we are looking for. All right, now check this. If we move the decimal point right to this point, the new equation that we will be having will be different because the digits after the decimal point will also be different. But you realize that if you move the decimal point all the way to this side right here, the new equation that will be forming will have the same digits after the decimal point as this first equation. So what I'll do is that I'll say equation 1 times 1000, simply because I want the decimal point to come somewhere here. So we are going to have 1000 m is equal to 431.431 up to infinity. And this will be our equation 2. Right, now we see that after the decimal point, the digits right here are the same as the digits right here. Therefore, we can subtract equation 1 from equation 2. So I will say equation 2 minus equation 1. So on the left hand side, we have 1000 m minus just m. So we'll be left with 999m, and this is equal to, now because all these digits right here are the same as these digits right here, they will cancel each other. So we'll be left with just 0 and 431. So 431 minus 0 will still be 431. And obviously we are looking for m, so we have to divide each side of the equation by 999. Then here also by 999. Clearly this and that will go, and we have m is equal to 431 divided by 999, and that is pretty much it. If you use a calculator for this, you'll still be getting this right here. Next, all right, now this is our next example right here. We have 0.16 with a bar on top of the 6. Now this bar right here simply means that the 6 is recurring. So basically this is the same as 0.1666 up to infinity. So let's go ahead and then change this to common fraction. Obviously we have to let something represent the fraction that we are looking for. Should be equal to 0.1666 up to infinity. Now this is our equation 1. Let's go ahead and then multiply equation 1 by 10. And if we do that, we are going to have 10x on the left, then on the right we are going to have 1.6666 up to infinity, and this will be our equation 2. Pretty nice. Now you realize that after the decimal point right here, the digits that are here are different from the digits here because of this one right here. So therefore we cannot subtract this equation from this, right? So what we will do is that we go through another step so that the digits will be the same. And to do that, I will just have to multiply equation 1 by 100 so that it will come somewhere here. Or you can multiply this equation by 10 so that it will come here. So I will say equation 1 times 100. And this time around, we are going to have 100x is equal to, this times 100 is going to be 16.666 up to infinity. And this will be our equation 3. Now let's compare equation 2 and equation 3. You realize that after the decimal point right here, we have 666 up to infinity. Then from equation 2, after the decimal point, we have 666 also up to infinity. That means that we can take equation 2 from equation 3 and we will be good to go. So I would say equation 3 minus equation 2. And this time around, we are going to have 100x minus 10x. That is just 90x. And this is equal to, now because these digits right here are the same as these digits, they will all disappear. All right, so we are going to have 16 minus 1, which is 15, and this implies that we have 90x is equal to 15. We are looking for x, so we will divide each side of the equation by 90 so that this and this will go. Now we have x is equal to 15 goes into itself 1 and then goes into 90 6 times. So we are left with 1/6. If you use a calculator for this again, you'll still be getting this. So that is pretty much it. All right, guys, in today's video, we will look at significant figures. And with time, you'll see me using SF for significant figures. So let's say we have these small numbers, A, B, and C. In fact, how many significant figures do we have in each? Before we start, I believe you are now starting, but pause the video and give it a try first. And if you get it wrong, don't worry. You use this example right here to explain everything. If you are done, let's get right into it. In fact, with this first example, we have two significant figures in it. What about the B? With the B, we have four significant figures. What about C? With C, in fact, we have 5 significant figures. But the question is, how did I come out with all these number of significant figures? Let's use this example right here to explain. Now, these zeros right here in front are known as leading zeros. So let me write it. They are known as leading zeros. And one key thing about leading zeros is that all leading zeros are not significant. So if you look at case 1 right here, all these are known as leading zeros, which are not significant. The only significant figures we have in this number right here is just 1 and 8. That is how come we had two significant figures for the whole of this. Now let's consider the second example. This right here, we also have leading zeros which are not significant, yet we had 1, 2, 3, 4 as significant figures. All right, so that brings us to this part. Now, these zeros right here are known as trailing zeros. Now, there are two important things about trailing zeros. Trailing zeros are significant if there is a decimal point. That is case 1. And case 2, trailing zeros are not significant if there is no decimal point. So with the first case, we can clearly see that with this example right here, we have trailing zeros in it. That is actually two trailing zeros, right? Now, because we have a decimal point right here, it makes these two trailing zeros significant. So to talk about significancy in this number right here, we have to obviously start from the non-zero right here, which is 1. So we have 1, 2, 3, 4. That is how come we have 4 significant figures. All right. Now let's consider this 0 right here. In fact, this 0 is between two non-zero numbers, that is 8 and 5. This is to say that all zeros between two non-zero numbers are significant. Therefore, this number right here is also significant. But the question is, how many significant figures do we have in this number right here? And to do this, in fact, we have to start counting from the left to the right, starting from the non-zero number. Remember, even if there is a decimal point right here, so these zeros are still leading zeros, of course. So we have 1, 2, 3, 4, 5, 6. So with this one, we have 6 significant figures. So the key thing to identify when it comes to significant figures, especially smaller numbers like this, you have to first consider leading zeros, zeros between two non-zero numbers, and trailing zeros. And like I said, two conditions. Trailing zeros are significant if there is a decimal point, right? If there is a decimal point. Again, trailing zeros are not significant if there is no decimal point. So now that we have these key things, we can just start solving examples. So I'll get rid of this quickly. Let's say we have 4.973, number like this. And maybe we want to leave this one in just one significant figure. How are we going to do it? Let's consider the question. So to leave this one in one significant figure, of course, we have to start counting from left to right. And if we start counting, this will be the one, right? Now, you just have to identify where you landed, which is 4 in our case. Then you consider the number that is next to that. The number that is next to the 4 right here is basically 9. And always, let's say the number that is next to the number that we landed on is x. Now, if that number is greater than or equal to 5, then we add 1 to the number that we landed. All right. Now, if that number next to the number that we landed is less than 5, then we are basically going to forget about it, right? So with this one, we see that we landed on 4. The number next to the 4 is 9, which is greater than or equal to 5. If that happens, then we are going to add 1 to the number right here. In the same way, if it is less than 5, then it means that we are going to leave it like that. We are not going to do anything to it. We just throw it away, right? So this 9 is more than 5, so we have to add 1 to this, making 5, and we are done. Of course, if you try to bring 0.000, remember these zeros are trailing zeros with a decimal point, which are also significant. So if we try to convert these to zeros, then actually we are talking about four significant figures right now. All right. Yeah. So now that we understand this one, with the same number, let's say we want to leave it in probably, let me say this is one significant figure. Now let's say this time around we want to leave this in two significant figures. Of course, we have to start counting from left to right. And to do that, we have 1, 2. We just landed on the 9 right here. Of course, don't just write the two of them, but consider the number that is next to that. And you can see that the number that is next to 9 is obviously 7. 7 is greater than 5, right? So we have to add 1 to this. And of course, if we add 1 to this, we are going to have 10. But we can't write all the 10 right here. So what we will do is that we just run it again, then we'll have 5.0. And this time around, this is going to be two significant figures. Now, the cool way to understand this one is that sometimes students make these mistakes. When they run and they get 10, they find it difficult to simplify. This is how to do it instead. Now, if you have a situation like that, you just have to write the two digits first, like this. So we have this. Then we want to add 1 to this 9. So basically, bring that 1 right here. And then do the basic mathematics. We have 9 plus 1, that is giving us 10. Of course, base 10, we can't write all the 10 there. So we write 0 remainder 1. Then we have a decimal point, bring it there, right? Then we have 4 plus the remainder, which is 5. So we have 5 here. So we have 5.0, which is two significant figures, simply because we have trailing 0 with a decimal point, which is also significant. See that? So pretty much simple. All right, so now that we have this idea, we can keep on doing some examples. So again, let's say we have 15.0073, and maybe we want to leave our answer or this number right here in three significant figures. How are we going to do it? Now, to leave this in three significant figures, of course, we have to start right from here. We have 1, 2, 3. We landed on this 0 right here. Okay, now the number that is next to this 0 is still 0, which is obviously less than 5. Therefore, this number in three significant figures is going to be, and this is in three significant figures, as simple as that. With the same number, let's say we want to leave this in probably four significant figures, then we are going to have 1, 2, 3, 4 on this number. Now, the number that is next to this 0 is 7, which is more than 5. So we add 1 to this one, then we will have 15.01. And this is in four significant figures. Pretty much simple, right? So I believe now if you're given any decimal number and you're asked to run it or leave it in a certain significant figure, basically you can do it. Now let's consider whole numbers. Let's say you are given a whole number and you are asked to, let's say we have 8, 7, 6, 0, 1, 6. In fact, this number is 876,016. And maybe we are asked to leave this in, let's say, two significant figures. Let's say we want to leave this in two significant figures. Of course, always we have to start from the left and then count to the right. So 2, we have 1, 2. We just landed on this 7 right here. And remember, the number that is next to the 7 is 6, which is more than 5. If that happens, then we will run it. We will add 1 to this. So we are going to have 8, 8 this time. But are we going to leave it like this? Remember, this number is somewhere around 800,000. So it means that if you leave it like this, which is 88, then you have obviously reduced the number from each state to a very small state, right? And that makes it wrong, right? So to do this, what you have to do is after changing this one or running the next number, you have to leave all these numbers in zeros. So we have 1, 2, 3, 4. I'll just put those zeros there, and you realize that still we are around 800,000. Okay, now the key thing you have to note here is that when it comes to whole numbers, after identifying your significant figures, you have to change the remaining digit to zeros. Unlike the decimal numbers where we forget about all the numbers after identifying your significant figures, with this one, of course, you have to change all the digits that are remaining to zeros. All right. Now, with the same example, let's say we want to leave it to maybe four significant figures. So let me write four significant figures. With this one, of course, we have to start counting. 1, 2, 3, 4, right? We just landed on this number right here. And we see that the number that is next to this 0 is obviously less than 5. So we are going to have 8, 7, 6, 0. Then we change this one also to zeros as well, which will be 0, 0. And of course, we are still in the range 876,000. Okay, now let's consider another example. Let's say we have, this time around, I'll use red marker. Let's say we have 200,553. So this is around million, right? 2 million. If I put comma here, we are around 2 million. And we want to run this one or leave this one in maybe four significant figures. Of course, this is going to be 1, 2, 3, 4. We just landed on this one right here. The number that is next to the 1 is 6, which is more than 5. So we have to add 1 to this, making 2002. Then we try to change all these to zeros so that we will have 0, 0, 0. And we can clearly see that still we are in the million color, right? So that is basically how to run whole numbers to a given significant figures. Now this time, let's consider numbers in the standard form or numbers in the scientific notation. Let's say we have 2.693 times 10 to the power, let's say 4. Let's say we have this number, right, in scientific notation, and we want to leave this in two significant figures. So two significant figures. Let's say we want to leave this in two significant figures. Now to do this, of course, don't pay attention to the 10 to the power something something. Don't pay attention to that, but just pay attention to these decimal numbers right here. Of course, with this, you start counting from left to right like we know already. So we have 1, 2. We just landed on this 6. The number next to the 6 is 9 more than 5. So we add 1 to this, making 2.7 times 10 to the power 4, and you are done. Now remember, we have a decimal point here. If you try to convert or change all these numbers to zeros, you are going to end up getting two trading zeros with a decimal point, which are also significant. So in this case, it is going to be 1, 2, 3, 4, four significant figures, which is obviously not two significant figures. Therefore, you are wrong when it comes to that, right? So you have to pay attention to that very well. Now, with the same number, we want to leave this in just one significant figure. To do that, we have 1 right here, right? Counting from this side, 1, we are on this number. The number next to that is 6, which is more than 5. We run or add 1 to this one, making 3. So we are going to have 3 times 10 to the power 4, and you are done. Okay, now if you put a decimal point like this without writing anything, it is still correct. But as soon as you add 0 to 8, it's not in one significant figure anymore. Therefore, we have 2 because of this 0. Trailing 0 with a decimal point, it is significant. So this is now in two significant figures and not one, right? So that is that. But you can choose not to bring the decimal point and you are still correct. Let's consider another number. Now let's say we have 0.0767, and maybe we want to leave this in just one significant figure. What is it going to be? Now with this right here, in fact, These are leading zeros which are not significant, so we have to start right from here. So 1, we are just landing on the 7. The number next to the 7 is 6 more than 5, so we have to add 1 to this, making 0.08, and you are done. Remember, these two zeros right here are here to help us maintain the value of the number. If you try to forget about it, remember this number right here is not even up to 1. If you forget about it like this, we are somewhere around 8 going, right? You have obviously added some numbers which are not supposed to be added to that. So to maintain the value of the number, of course, we have to bring 0.00. After all, we know that these are leading zeros and they are not significant. All right, now let's look at how we can represent proper fractions on the number line. We have 3 over 4, 2 over 3, negative 1 over 6, negative 5 over 6. Now, before we delve into this, let's pay attention to this. All proper fractions are found between 0 and 1. If it is negative, then obviously it's going to be within from 0 to negative 1. So now that we have this idea, let's begin. With the first one, we have 3 over 4. Now to do this, the key thing is that we divide this interval right here by the denominator right here, which is 4. So it means that with this interval from 0 to this one right here, we have to divide it into 4 equal parts. And from there, we can locate this fraction right there. So let's see. This is 1, 2, 3. So this is what we have. And obviously, the first point right here is going to be 1 over 4. Then this will be 2 over 4, which is still 1/2. Then here will be 3 over 4. So for 3 over 4, we have it right here. And because we are not looking for these two fractions, you can actually get rid of them. But if it's there, you can also let it be there. Right, so we are done with this one. Let's focus on 2 over 3. Let me get rid of this quickly. Now, for 2 over 3, as we know already, we have to divide this interval by the denominator right here, which is 3. So we are going to divide that. We have 1, 2, and 3. So that this first one here will be 1 over 3. This one will be 2 over 3. So this is where it's going to be. Very simple. Now let's consider these two fractions. Actually, let's do this one first because this is a little bit difficult than this one. Now, because this is a proper fraction, obviously it's negative. So it's going to fall within this range from here to here. So what we are going to do is that we're going to take this number right here and divide this interval by the number there, which is 6. So let's do that. We have 1, 2, 3, 4, 5. So that is that. So the first one here is going to be negative 1 over 6. This is going to be negative 2 over 6. This is negative 3 over 6. This is negative 4 over 6. And this point right here will be negative 5 over 6. Because we are not interested in these, obviously we can get rid of them, right? So that it will look nicer. So let me do that really quick. Yes, so this is where negative 5 over 6 is going to be. So now that we have these intervals, obviously we can locate what negative 1 over 6 is. That is going to be just here, negative 1 over 6. Pretty much simple, huh? All right, now let's look at how we can represent improper fractions on the number line. We have 3 over 2, 7 over 2, negative 4 over 3. So let's begin. Now, before we can represent any improper fraction on the number line, first of all, we have to rewrite them in mixed numbers. So for this right here, it is the same as one whole number 1 over 2. This is the whole part, this is the fractional part. And actually, we can rewrite this as 1 plus 1 over 2. So what we have to do first is to locate the whole number on the number line. Then after that, we add the 1/2 to it. That is pretty much simple, huh? So let's see. We have 1, which is this point right here. Then, as we know from the previous one, to do this 1/2 right here, we need to divide this interval into two equal parts because of this two right here. So basically, we have to divide it, and it's going to be somewhere here. So this point right here is now going to be 3 over 2, like that. So it's going to be here. This is the one, and this right here, from here to here is now the zero point 0.5. So we are basically done for this one. Now let's consider 7 over 2. So 7 over 2 is also the same as 3 whole number 1 over 2. Pretty simple. 2 times 3 is 6 plus 1, 7 over 2. So it's almost the same thing. Then we split this. It is the same as 3 plus 1 half. So what we will do is that we will first locate the whole number on the number line, which in this case is the 3 right here. So 3 is this point right here. Then plus 1 half, which basically means that we have to divide this interval into two equal parts, which is also going to be the middle right here. So from 0 to this point right here is now going to be 7 over 2. As simple as that. Now let's look at how we can represent this negative 4 over 3 on the number line. So first of all, we write this as a mixed fraction, which is obviously going to be negative 1 whole number 1 over 3. And we can actually split this way. It's going to be negative 1, then minus 1 over 3. And first of all, we have to locate this negative 1 on the number line, which is this point right here. Then plus minus 1/3, meaning from this interval negative 1 to negative 2, we have to divide it into three equal parts, which is going to be this and that. There we go. So this point right here is actually negative 1 over 3 if we are from negative 1, right? But remember, we are from this point right here, 0, all the way to this point, which is obviously going to be negative 4 over 3. And that is pretty much it. Now let's look at how we can locate irrational numbers such as square root of 2 and square root of 3 on the number line. Let's get right into it. Now to locate square root of 2 on the number line, first of all, we have to measure 1 unit to the right. So it means that from this 0 right here to here is 1 unit. Then we have to also measure the same unit up, just like this. So from here to this point is also 1 unit. Then we just join them with a meter rule like this. So here is also 1 unit. Then we have to join these 2 points from the origin all the way to this point right here. And this time around, you see we have a right angle triangle right here. This distance is 1, this is also 1. Obviously, we have to get this distance. Let's call it x for now. In fact, from Pythagoras' theorem, we know that the longest side, which is the hypotenuse, squared is actually equal to the squares of the other two sides, which is 1 squared plus 1 squared. And obviously, we have x is equal to square root of 1 plus 1, which is 2. And this is what we have. So therefore, this x right here is now square root of 2, of which we are looking for. And this time around, all we need is a compass. We just measure this distance right here, and in a way, we now have a circle. So we just draw an arc to cut across the line like this, and this is going to be the point from here to here, which is now square root of 2. Now we have a circle with a radius of root 2. So in case we need negative square root of 2, then it means that we have to construct an arc like that, so that probably is going to be somewhere here because it's not drawn to scale, Now let's consider square root of 3. We want to locate that on the number line. To do this, obviously we know that from here to here is square root of 2. So we just have to measure 1 unit up, which will be somewhere here, cool. Then we draw a straight line from the origin to meet this point, then the same way we draw it down like this. So again, we have a right angle triangle here. Now let's call the distance from here to here maybe y, so that we are going to have y squared is equal to, from here to here is square root of 2 squared, then plus from this distance to this distance, which is 1. So we are also going to have 1 squared, which is still 1. So we have y is equal to square root of this whole thing. We'll cancel out that. We have 2 plus 1, which is 3. So for square root of 3, you just take your compass, stand on the point 0 right here, open it up to this point, and you just draw your arc to cut across this line like this. And this point right here, from here to here, is now square root of 3. Now let's say you want to locate negative square root of 3 on the number line. Now we have square root of 3 right here. So with the same radius, you make an arc right here to get your negative square root of 3. In the same way, you can do that to square root of 2. If you need square root of negative 2, square root of negative 2, all you need is the same radius. You make an arc right here to get your square root of negative 2. All right, now let's look at standard form. Standard form is also known as scientific notation. Standard form has the form a times 10 to the power n. This is the form of the standard form, and n is an integer. This n right here is an integer, and this a should be within this range, less than 10, and it should be greater than or equal to 1. So this is the whole idea about standard form or scientific notation. And like I said, it is used to make numbers manageable. Let's say we have this number right here, 9181,000,000. If I put the comma like this, we are around somewhere 9 billion. The number looks a little bit scary, but with the idea of scientific notation or standard form, we can make this number right here manageable. In fact, we can rewrite this as 9.181 times 10 to the power. In fact, we want to move a decimal point to this place. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So the power right here is going to be 9. Now, if we compare the whole of this to this form, we can clearly see that our n is the 9 right here. Then a is 9.181, which is in this range. We can also have a very small number. Let's say we have 0.000123. It's a very small number, and we can write this in a standard form. This is basically 1.23, then times 10 to the power, the number of times we move. In fact, we are going to move the decimal point all the way to this point right here. So we have 1, 2, 3, 4. So to the power minus 4. And the key thing you have to pay attention to here is that if you move a decimal point from left to right, then it means that the power is going to reduce and the number right here is going to increase. In some ways, the a is going to increase if you move the decimal point from the left to the right. In the same way, here we assume that we have 0.0 right here. And if we move this decimal point from the right to the left like this number is going to reduce, but the power is going to increase. So that is the whole idea about standard forms. All right, now we have these examples here. Let's go ahead and then write each of them in standard form, starting from the first one. So a is actually going to be, in fact, the decimal point is now here, and we want to write it in standard form. So basically, we have to move it all the way to this point, because the number right here should, in fact, be in this range. That is a less than 10, and it is greater than or equal to positive 1. So this is the range. Always, this is our reference point. So let's see. The decimal point is here, so we want to move it to this side. We have 1, 2, 3. Now remember, if you let it come here, then it means you are going to have 22 point something, which is not in this range. It should be between the first two non-zero digits, so which is 2.2, then times 10 to the power, the number of times we moved, 1, 2, 3. So to the power minus 3. In fact, if you are moving all the way to the right, then the number is going to increase, but the power right here is going to decrease. So this is 8. Now let's consider the b. So b, the decimal point is here. Now we have to move it all the way to this point so that our a will be in the range. If you bring it to this side, then it means you are going to have 50 point something, which is going to be more than the range right here. So basically we are going to have 5.003. Because here we have a non-zero number here, it means that we have to write all of them. So we have 5.003, then times the number of times we move. We have 1, 2, 3. So it's going to be here. So we have times 10 to the power minus 3, and we are done. So this is B. Now let's come to C. The decimal point is here. Now check this out. If we move it to this side, then it means that we are going to have a very big number times 10 to the power something, which will be off range, right? So we would like to bring it to these two non-zero digits right here. So we want to move it all the way to this point right here, which will be 3.56. And don't forget, these are not 00. We have 01, so we have to add all of them. 01, then times 10 to the power the number of times we moved. We have 1, 2. So we are going to have positive 2 since we are moving from right to left. And remember, the power is going to increase, then the number right here, which is our A, is going to decrease. So that is pretty much it for C. Now let's consider the last one, which is D. Now for D, of course, let's assume that the decimal point is here. We want to move it all the way to the last two non-zero digits. So we have 1, 2, 3, 4 right here. So we are going to have 5.5. Because all these are zeros, you can choose not to bring it. And remember, if you bring it, you are not wrong, but so times 10 to the power the number of times I moved, 1, 2, 3, 4. So we are going to have to the power 4. And that is pretty much it. All right, now let's look at how we can add or subtract numbers in standard form. The first one, we have 2.8 times 10 to the power 4 plus 1.6 times 10 to the power 4. So let's begin. A right here. In fact, a cool way to do this is to write it in this form. We have 2.8 times 10 to the power 4, then plus 1.6 times 10 to the power 4. As simple as that. Now, don't worry about this 10 to the power 4, 10 to the power 4. Check it this way. Let's say we have 2x plus, let's say, 5x. Obviously, we are just going to add 2 and 5. Then we attach the result with one of these variables. So it's going to basically be 7x. It's the same thing. So if you compare this right here to what we have here, this 2 is basically this number, and this variable, which is x, is just 10 to the power 4, 10 to the power 4. So that means we don't have to do much about this x right here. What we have to basically do is to combine these two numbers right here. Then after that, we attach one of the 10 to the power 4 to the results that we get. So basically, this is going to be there, 10 to the power 4. Then we sum this one. We have 8 plus 6, that is 14. So we will write 4 remainder 1. Then 2 plus 1 is 3 plus 1 is 4. But don't forget, we have decimal point right here. And we are done. So simple, right? You see that this number right here, which is our A, is in the range. That is, A is less than 10 but greater than or equal to 1. Now, if you found out that this number is not in the range, then you have to change it to this range by either moving a decimal point to the right or the left. Pretty simple. Okay, so I'm gonna get rid of this and then focus on the B part. Now let's consider the B. In the same way, we can write this as 2.5 times 10 to the power negative 4, then minus 1.6 times 10 to the power minus 4. Then in the same way, we have to still keep any of these two 10 to the power minus 4. So we have 10 to the power minus 4. Now we have 5 minus 6. That seems impossible, so we need to borrow. You go and borrow 1 from here, and this time you have this one to be 15. 15 minus 6 is 9. So I'll put a decimal point right here. Then this time we are left with 1 over here. 1 minus 1 is 0. Now you see that this number right here is not in the range, that is a less than 10 but greater than or equal to 1. You see that this number right here is less than 1. Therefore, it is not in the range. So what we have to do is that we move the decimal point to the right so that the number will be in the range. So this is what I mean. Now the number right here is actually going to be 9. That means we are moving the decimal point to this place so that we have 9 times 10 to the power. Remember, we moved it to this place, so the power is going to decrease by 1. Then we still have this right here, that is times 10 to the power minus 4. So finally, we are going to have 9 times 10 to the power minus 5. As we are increasing the value here, the power is decreasing, as you can see right here. So that is that. This is the final answer for this right here. Now let's consider this nice example here. We have 2.8 times 10 to the power 4 plus 1.6 times 10 to the power 3. Now note this carefully. Before you can add two standard forms, basically the powers have to be the same. The powers have to be the same. Here we have a power of 4, here we have 3, and they are not the same. In order for us to add them, we have to first make them the same before we can add them. But the question is, how can we make them the same? Check this out. You realize that if I move the decimal point all the way to the left, the number right here is going to decrease, but the power is going to increase. So I will just have to keep this. We have 2.8 times 10 to the power 4, then plus, this time I'm going to move the decimal point here. And if I do that, we are going to have 0. This right here. So we have 0.16, then times 10 to the power. This time the power is going to increase by 1. And now we can clearly see that the powers are the same. Therefore, we can easily combine them. So we are going to have 2.8 times 10 to the power 4. Then if you're doing this, be careful. Make sure this number comes below this number right here. So we will have 0, then you put your decimal point nicely, then this number will come below this one. So we have 1 here, and this will come somewhere here, then times 10 to the power 4, and this time we can comfortably add them. Okay, so as we know already, we will have 10 to the power 4 here like that. Then this side we have nothing is here, so we assume that it is 0. So we have 0 plus 6, which is 6. Then we have 8 plus 1, that is 9. And we have our decimal point there. Then 2 plus 0, which is still 2. And we are done. All right. So basically, this is how to add or subtract numbers in standard form.